Okay, now let's move on with the tetrahedral complex under the consideration of the pi bonding. When we started to look at this, that was actually this slide, so that we already discussed. So we said that in a tetrahedral complex, we do not really have exact pi bonding because the way the pi orbitals in the ligand are oriented does not provide exactly pi overlap with the metal d orbitals, but nonetheless there are interactions and we can approximate these as pi interactions. So when we have a tetrahedral complex, and again we assume carbonyl as the ligand, how many ligand orbitals do we have to consider? So each carbonyl ligand would have two bonding pi orbitals and two interbonding pi orbitals. And we have overall 4 ligands, so that would mean that we would overall need to consider 16 ligand orbitals, and we have to group these 16 ligand orbitals to form ligand group orbitals. Okay, so now 8 of them would be pi, and 8 of them would be pi star. And our task would now be to determine their symmetry types, and we can do this using the symmetry adapted linear combination of atomic orbitals method. So we would again have to use the orbital swapping method and then apply the reduction formula in order to get the symmetry types. So now, what would be these symmetry types in this case? So for both the pi and the pi star orbitals, we would get 2 ligand group orbitals that have the symmetry type E, 3 ligand group orbitals that have the symmetry type T1, and 3 ligand group orbitals that would have the symmetry type T2. And these together would give 8. Okay, we would have 2 sets of these 8 ligand group orbitals, which would give overall 16. So with this information in hand, we can now construct our molecular orbital diagram under the consideration of pi bonding. Now you see here again the molecular orbital diagram that we have constructed in the last class that considers the sigma bonding only. I just briefly go through this MO diagram as a little refreshment. So we said that we have here these 4 bonding molecular orbitals in which we have all the electrons coming from the ligand, and then we have this 1e and that T2 molecular orbital, and these would represent the metal d orbitals in a tetrahedral ligand field, and the energy difference between these would be our delta T. So now in addition to that, we would have here this 2a1 interbonding orbital and that 3t2 interbonding molecular orbital. So now how will that change as we consider pi bonding in addition to sigma bonding? Now again, there can be 2 cases, okay? The ligand may act as a pi donor, or the ligand may act as a pi acceptor. So for the pi acceptor case, the interactions of the interbonding ligand group orbitals with the metal orbitals would be far stronger than the interaction of the bonding ligand group orbitals with the metal, and therefore the latter could be neglected, and we would need to consider only the interactions of the interbonding orbitals. So this is the typical situation that you have in a carbonyl ligand. So carbonyl is a typical pi acceptor in metal carbonyls. pi accept electrons from the metal to the ligand. So now a tetrahedral carbonyl is the nickel tetracarbonyl. And in the nickel tetracarbonyl, you have, well, 10 additional electrons to consider, which are in the 3d and the 4s orbitals. So now let's construct the additional pi molecular orbitals using the interbonding pi star ligand group orbitals. So we saw previously that 2 of them have the symmetry type E, and 3 of them have the symmetry type T2. So now we saw that we also have T1 ligand group orbitals, right? But we do not need to consider them here. That is because we do not have any T1 metal orbitals, and therefore any T1 ligand group orbitals would remain non-bonded. So let us construct additional molecular orbitals using these E and T2 orbitals. So we can, for instance, start out with the E. So these E orbitals would interact with these E orbitals here. So we would expect a bonding pair of molecular orbitals and an interbonding pair of molecular orbitals. So you see that previously the E orbitals of the metal were completely non-bonding, and we would expect that, well, these orbitals now would become bonding, and there would be a pair of interbonding molecular orbitals of E symmetry as well. Okay, now let's just do this. Okay, so these orbitals here become bonding. Okay, and then we create another pair of interbonding E orbitals as well. Okay, now we are done with our E orbitals. In the next step, we need to consider the T2 orbitals. So now you see that we have both d orbitals as well as 4 p orbitals of T2 symmetry, and they can interact both with these T2 ligand group orbitals. Okay, so what would we expect? We would expect that well, these T2 orbitals here, which currently are approximately non-bonding, not exactly non-bonding, will become bonding, and that we have an additional, well, triplet of interbonding T2 orbitals in addition. Let's just do this. Okay, so I move these orbitals here down, and we create an additional triplet of T2 molecular orbitals, which is interbonding. Okay, so now it's also worthwhile to double check that we have the right number of molecular orbitals. I always told you that the number of molecular orbitals must always be equal the number of orbitals from which they have been constructed from. So we can, for instance, count the number of T2 orbitals that we have. So we have here these 3, and these 3, and these 3, and these 3. So that gives overall 4 triplets. Okay, so we would need to find these triplets in our molecular orbital diagram again. So we see we have this one, the second one, third one, and the fourth one. Okay, everything is good. So now for the E orbitals, it should be the same. We have this pair here and this pair over there, so that gives 4. And we have here this pair and that pair over there, so that gives also 4. And then, of course, for the A1 type orbitals, same has to be true. So we have, in this case, only 1 over here and 1 over there. So we have this bonding here and this interbonding one over there. So we see that the number of molecular orbitals in the middle is equal to the number of metal orbitals plus the number of ligand orbitals. So everything needs to be correct. So now let us see what actually happened to our delta T. Okay. So we see that our delta T has actually increased. Okay, I can show you this again by going actually backward. So originally we started out here. So we made this orbital bonding. And we made this orbital here bonding to. But the decrease in energy of the E orbitals is greater than the decrease of the energy of these T2 orbitals, so that our delta T increases. However, it does not increase very much, just because the energy of both orbitals is being lowered. So that means that in contrast to the octahedral case, where we got a strong increase of delta O through the pi interactions, pi acceptor interactions to be precise, this is not the case for the tetrahedral complex. Here, we only get a small increase of delta T. So this can serve as another explanation of why it is possible to make high spin and low spin complexes for octahedral molecules, but not for tetrahedral molecules. For tetrahedral molecules, we only observe high spin, and that's because that delta E never becomes so large so that the energy difference can be, the spin pairing energy can be overcome. All right, so what else is to consider? We still have to consider the number of electrons. Now in our example, we have formed the nickel tetracarbonyl, which is known to be a stable molecule. And now we would have to consider 10 electrons of the nickel, because in the nickel tetracarbonyl, nickel is in the oxidation state 0. So therefore, we now have to fill 10 additional electrons into the molecular orbitals. Okay, so now this would make the 1e orbitals completely full, as well as the T2 orbitals completely full. So now we can again see why our molecule is being stable. That is because we have only bonding molecular orbitals being filled, and all the anti-bonding molecular orbitals are being empty. Again, we can also see why the 18 electron rule holds, because when we count the valence electrons in nickel carbonyl, we would see that there are 18. We can again do this by either using the oxidation state or the neutral atom method. But when we count the number of bonding electrons in our complex, we see that it's also 18. Okay, so we have these 6, then that's 8, and that's 10, and that's 12, and that's 14, 16, 18 electrons. So again, the molecular orbital theory, the ligand field theory, explains why the 18 electron rule holds. It's because all 18 electrons are in bonding molecular orbitals, which makes our molecule stable. So now we have to consider the other case also, which is that we do not have a pi acceptor, but we have a pi donor. So typical pi donating ligands are halogenide ligands, like chloroligand, and a molecule, a tetrahedral molecule that has chloroligands would be, for instance, titanium tetrachloride. So let us construct the qualitative molecular orbital diagram for titanium tetrachloride under the consideration of pi bonding, assuming now that the chloroligand acts as a pi donor. So when we consider the chlorine as a pi donor, then we can neglect the anti-bonding ligand group orbitals, and we only need to consider the bonding ligand group orbitals. Okay, so now let's add the relevant bonding ligand group orbitals. Again, this would be the E and the T2. There would be 3 T1s in addition, but we don't need to consider them because we don't have any metal orbital that has T1 symmetry. So we can again combine orbitals of the same symmetry type and see what happens. So now these E orbitals will now interact with these E orbitals. So the bonding pi orbitals are energetically lower than the pi star orbitals, which we previously considered. They actually, and it must be energetically somewhat below the highest occupied molecular orbit that makes the sigma bonding, because we know that the pi orbital, as in the molecular orbital diagram, are always below the homos that provide for the sigma bonding. So in this case, we have a chloroligand. In this case, our HOMO would be considered the p orbital that would make the sigma bonding with the titanium, and the 2 p orbitals that stand perpendicular to that pz orbital, the px and the py orbital, would be those that can make the pi bonding. Okay, now let's combine the respective molecular orbitals. So now the interaction between these E will actually move this formerly non-bonding E metal, these formerly non-bonding metal d orbitals up, and we would create a bonding pair of E orbitals as well. Okay. Then we have 4 E-type molecular orbitals constructed from 4, 1, 2, 3, 4 E orbitals, and so the numbers are identical. So therefore, everything must be right. So now, what about the T2? So now these T2 would interact with the 3D T2 and also somewhat with the 4p T2, even though not much, because the energy difference between the 4p T2 and the T2 ligand group orbitals is pretty large. Okay, now what will happen in this case? Well, this orbital here, or these 3 orbitals here, will actually move up in energy. Okay, and we create an additional triplet of bonding molecular orbitals as well. Okay, now what else is to do? Well, we have now 10 additional electrons to consider, which are in the ligand. Okay, so now these 10 electrons would need to go into this bonding T2 and the bonding E1 that we have created. Okay, so now do we have any additional electrons to consider that are coming from the metal? In this case, the answer is no. That is because in titanium tetrachloride, the titanium is in the oxidation state +4. So in the neutral state, titanium is in the group 4. That means neutral titanium has 4 valence electrons. And if we remove these 4 valence electrons, well, the titanium has no longer any valence electrons. It's a D0 ion. Okay? Therefore, we do not need to consider any additional electrons. Okay, So now we can analyze what happened to our delta T because of the pi donor interactions, and you see that it has actually decreased. Okay, so like in the octahedral case, the pi donor interactions lead to a decrease of delta O. The pi donor interactions of in the tetrahedral case lead to a decrease of delta T. Yeah, this is summarized here. So now we can discuss again this result in the context of the 18 electron rule. So now when we count all these electrons, and these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so again we have 18 electrons. But it's worth mentioning that if we did the electron counting on the titanium tetrachloride using the oxidation state method or the neutral atom method, we would not get 18 electrons. Okay, that is because the titanium wouldn't contribute any electrons, and the chloride ions would contribute 8 according to the oxidation state method, so that would give only 8. And you'd actually see these 8 electrons here in these orbitals that make the sigma bonding. So that means that the electron counting method actually only accounts for sigma electrons. Okay, if you wrote the structural formula of titanium tetrachloride, right, we would write 4 single bonds between the titanium and the chlorine. So we would see only these 8 electrons, and these electrons would also be the only electron that would be counted. So our complex, therefore, appears as highly violating the 18 electron rule, because the electron counting only accounts for the sigma bonding here. But actually, if you take into account the possibilities of pi bonding also, we would even arrive at 18 electrons as well. Now we also clearly understand why the complex is stable in this form also, because, well, all bonding molecular orbitals are being filled, as you can see here, and all anti-bonding molecular orbitals are being empty, and that's, of course, always the perfect situation for the stability of the complex. Okay, so this is what I wanted to say about tetrahedral complexes. I know that this is a little bit a more complex chapter, so I wanted to ask at this point if there are any questions before I move over to the next example, which will be a square planar complex, which will actually be even more complicated. So are there any questions at this point? Okay, no questions. Then let us move over to the last example in ligand field theory, which will be this square planar complex of a 4th period transition metal. So we again have to apply the symmetry adapted linear combination method systematically. So first we need to be clear about the point group, which is D for H in this case. So we need to determine the symmetry of the metal frontier orbitals. In order to do this, we need to look into the character table for D4H. So the character table for D4H is here. What are our metal frontier orbitals? Well, again, there would be the 4s. The 4s orbital would have the totally symmetric symmetry type, which is in this case A1G. You can see this here. Then next, we need to consider the p orbitals. We can start, for instance, with the 4pz. So you can see that z can be found here in the character table. So therefore, the symmetry type would be A to U, right? So then there would be the px and the 4py. You see that x and y, actually here in the character table, you see that they are doubly degenerate and belong to the symmetry type EU. Next, we need to consider the d orbitals. So we can, for instance, look at the 3dxy first. You see xy is appearing here. So that belongs to the symmetry type B2G. Next, we can look at dxyz and dxz. So you can see both of them here. Okay, and they have the symmetry type BG. They're also double degenerate. And then we need to consider the 3dz square. So this one, you find 3dz square, you can actually find here. Okay, so this has A1G symmetry type. And last but not least, we have the 3dx square minus y square. You see that this orbital is being here. Sorry, no, this is x squared plus y squared. So this here is x squared minus y squared. So this is the correct line, which has the symmetry type B1G. Okay, so you see you have a lot more symmetry types to consider, and that is because of the relatively low symmetry of D4H in comparison to the symmetries that we've previously worked with, the TD and the OH symmetry. So we have less many degeneracies, and for that reason that we have more different symmetry types to consider, and that will now lead to a more complicated molecular orbital diagram. All right, so next we need to look at the ligand. So in this case, we won't choose a carbonyl ligand as an example, but a related cyanoligand, simply because carbonyl ligands are not known to make square planar complexes, but cyanoligand can do this, and with help of the ligand field theory, we can even explain why this is, and we'll answer this question a little bit later. So that means, again, that first we need to be clear about, well, what's the molecular orbital diagram of the cyanoligand, and then select the highest occupied molecular orbital suitable for sigma bonding. So the cyanoligand is isoelectronic to the carbonyl ligand. The nitrogen has one electron less than the oxygen, and we compensate that electron by giving the ligand a negative charge. Like the carbonyl ligand, the cyanoligand is a linear molecule belonging to the point group C infinite V, and nitrogen is the neighbor atom to oxygen. Therefore, our molecular orbital diagram for the cyanoligand looks very similar to the molecular orbital diagram of our CO ligand. The only difference is actually that because the smaller electronegative difference of between carbon and nitrogen relative to carbon and oxygen, the 2s of the carbon and the 2s of the nitrogen are closer in energy, and the energy of the p orbitals of the carbon and the energy of the p orbitals of the nitrogen are also closer in energy. But the symmetry is the same, and the number and type of molecular orbitals are also the same. So that means, like in the carbonyl ligand, this orbital here, the 3A1 molecular orbital, which is the HOMO, will be the ligand, will be the one suitable for sigma bonding. So like in the case of the carbonyl ligand, this molecular orbital represents the electron lone pair at the carbon, and it's localized primarily at the carbon because it has a somewhat interbonding nature. So like in the carbonyl ligand, also in the cyanoligand, the carbon is the reactive end and not the nitrogen. So what is next to do? Well, in the next step, we need to determine the symmetry types of our ligand group orbitals. Okay. So now we have to consider how many of these homos we have. Well, we have 4 ligands, 4 cyano-ligands. Therefore, we would expect 4 ligand group orbitals. And we would need to determine the symmetry type of these 4 ligand group orbitals using the orbital swapping method and the reduction formula. So that will result that one ligand group orbital has A1 symmetry, 2 of them have EU symmetry, and B1 and one of the last one has B1G symmetry. Okay, so now with this information, we can construct the molecular orbital diagram of the square planar complex for sigma bonding. Okay, we have our metal orbitals, the 3D, the 4s, and the 4p, and we write them according to energy and assign the symmetry types respectively. So then, in addition, we have the ligand group orbitals, 4 of them, and we write them according to energy and assign the respective symmetry types as well. Now again, we only need to combine orbitals of the same symmetry type. So we can, for instance, start with A1G. Okay, so we have one A1G here. We have another A1G over there. And also one of our ligand group orbitals has A1G symmetry type. So that should actually be blue here. So how many molecular orbitals, if A1G symmetry, will that give? Well, it will give 3. We can approximate that. One will be bonding and have low energy. One will be interbonding, having high energy. And one will be approximately in the middle, which is approximately non-bonding. Maybe weakly interbonding or weakly bonding also, we can't determine this from our qualitative considerations. Okay, what is the next step? So the next step would be to go to the next symmetry type. So for instance, we could choose the B1G symmetry type. So we have one d orbital of that symmetry type and one ligand group orbital of that symmetry type. That gives one bonding molecular orbital and one interbonding molecular orbital. Okay, so now we need to move on to the next symmetry type. So for instance, we'd go to the symmetry type E1U. So 4p orbitals have that symmetry type. There are 2 ligand group orbitals that have that symmetry type also. So that gives 2 doubly degenerated bonding molecular orbitals and 2 doubly degenerate interbonding molecular orbitals. So, well, what is left? Well, we see that the B2G orbitals of the metal, they do not find a partner and they remain non-bonding. And the two EEG type 3D orbitals also don't find a bonding partner over here. So they also remain non-bonding. And we have to write them with the same energy into the molecular orbital diagram. So further, we see that one of the p orbitals, namely the pz orbital here, which has A2U symmetry, also remains non-bonding, and we have to write it accordingly into the molecular orbital diagram. All right, so now what is left to do? Well, we have still our electrons that we need to fill. So again, we consider our bonded dative bond. The ligand group orbitals are being 4, containing 8 electrons, and we must fill these 8 electrons into the most bonding molecular orbital. So this fills the 1A1, the 1B1G, and the 1EU. Any metal D electrons would need to go into either the B2G, the EG, the 2A1G, or the B2B1G, depending on how many D electrons that we have. So generally, we find though that, well, we can again explain the shape of the complex well, because all our 4 sigma bonds would be explained, and also therefore the square planar shape be explained, because all our 8 electrons are in bonding. Coming from the ligand are in bonding molecular orbitals. So now we can again say that any metal D electrons that may be present would need to go into the I said this before, B2G, EG, 2A1G, or B1G orbitals. So we could again say that, well, these orbitals here are actually the metal D orbitals that split in energy due to the presence of a square planar ligand field. Okay, so these 3 orbitals would really be exactly non-bonding, would exactly represent the dxy, the dxz, and the dyz. So these molecular orbital, this molecular orbital here would represent the dz square in the square planar ligand field. So this molecular orbital is of course not exactly a dz square orbital, because also influences from, well, that 4s in that ligand group over here. But you see that this orbital here is approximately non-bonding and energetically relatively close to the d orbital of A1G. Therefore, it makes sense to approximate it as a dz square orbital in a square planar ligand field. So last but not least, we have here this arm to consider. So the 2B1G represents the d x square minus y square in a square planar ligand field. It has been made from, well, the dx square minus y square of B1G symmetry and a ligand group orbital of B1 symmetry. So also this one is energetically relatively close to this dx square minus y square. Therefore, in good approximation, we can say that this is still a dx square minus y square, but it is in a square planar ligand field. Therefore, it is somewhat different in a sense. Okay. So now I see here again the analogy between ligand field theory and the crystal field theory. Just like the metal d orbitals split in energy in a square planar crystal field, the d orbitals also split in energy in a square planar ligand fields. The results are, however, not exactly the same. So the results are exactly the same for the dx square minus y square and the dz square orbital. The ligand field, so in the crystal field theory picture, we saw that the dx square minus y square has the highest energy, and the dz square has the second highest energy. However, in the crystal field theory, the energies of the dxy and the dxz and the dyz were not exactly the same. We said that the dxy had a somewhat higher energy than the other two, just because the dxy lies exactly in the square plane, while the other twos do not and have strong z components. So now, why are these in the ligand field theory exactly the same? So this is because in the ligand field theory, we only consider if positive and negative interferences exactly cancel out or not. And if they cancel out or not, they are exactly non-bonding. We are not explicitly working actually with electrostatic interaction. So crystal field theory works with electrostatic interactions. The molecular orbital theory actually does not really do this, but it constructs the molecular orbital diagrams based on the interference of the orbitals with each other. Treats them as wave functions. All right, so now we are considered with the sigma bonding. Certainly, we also need to consider the pi bonding in addition. So now we need to be clear first, well, which orbitals to consider for pi bonding. And in this case, the situation is more complicated in the previous cases, because now the pi orbitals in the ligand are symmetrically not equivalent anymore. So we have to actually distinguish between so-called parallel ligands and parallel pi orbitals and perpendicular pi orbitals. So first of all, let's consider how many orbitals we need to consider overall. So each cyanoligand has 2 pi orbitals, and if you have 4 cyanoligand, that gives 2 times 4 equal to 8. But it also has 2 pi star orbitals each, and if you have 4 cyanoligand, that gives also 2 times 4 is equal to 8. So now, like I said before, we need to distinguish between pi orbitals that are perpendicular to the xy plane and pi orbitals that are parallel to the xy plane. So we see here the square planar complex within the xy plane. And you see here the pi orbitals that are perpendicular to the xy plane. You see the 1, 2, 3, 4 ligands here. And in blue, you see actually the pi orbitals. And you see that for each ligand, 1 lobe lies above the plane and 1 lobe lies below the xy plane. And that's true for all the 4 ligands. And we call these kind of orbitals orbitals that are perpendicular to the xy plane. So how many orbitals do we have? Well, we have 1, 2, 3, 4 bonding ones, but in addition to that, of course, we also need to consider the 4 anti-bonding ones. So this will give overall 8. Okay. So now, in addition to that, we need to consider the orbitals that are parallel to the xy plane. Okay, so these are the pi orbitals here. Okay. So now you see that these pi orbitals here lie within the plane. we can also say that they're parallel to the XY plane. So again, there are 1, 2, 3, 4 bonding ones to consider, and 4 inter-bonding ones to consider as well. Okay. So in the next step, we need to determine all the symmetry types of these different orbitals, the perpendicular ones and the parallel ones. All right. So for the perpendicular ones, we have for the bonding ones the symmetry type A to U plus EG plus B to U. That means of the 4 bonding perpendicular pi orbitals, 1 has A to U symmetry, 2 have EG symmetry, and the last one has B to U symmetry. And the symmetry types for the pi star orbitals being the same, 1 has A to U symmetry, so 2 of them has EG symmetry, and the last one has B to U symmetry. So the parallel ones are symmetrically different from the perpendicular ones, therefore they have different symmetry types. So the bonding 4 have the symmetry type A to G plus EU plus B to G. That means 1 of them has A to U symmetry, 2 of them has EU symmetry, and the last one has B to G symmetry. The interbonding ones have the same symmetry. 1 has A1G symmetry, 1 EU symmetry, and the last one has B2G symmetry. Okay, so now we have determined symmetry types of all our ligand group orbitals that are relevant for pi bonding. So now we can construct the molecular orbital diagram under the consideration of pi bonding. So now to do this, we need to be clear which orbitals of the metal interact with which orbitals of the ligand. You see here again all the metal d orbitals. You see here the parallel ligand group orbitals, and you see here the perpendicular ligand group orbitals and the symmetry types. Then we see that the 3D XY has a B2G symmetry and will interact with the B2G parallel LGOs. The 3D XZ and the 3D YZ have EG symmetry. They can interact with the EG orbitals of the perpendicular LGOs. The DZ square orbital, which has A1G symmetry, does not find a partner, so it's not involved in the pi bonding. Also, the 3dx square minus y square is not involved in the pi bonding. However, now we have to consider in addition the 4s orbital that has A1G symmetry. As a consequence, it's not involved in the pi bonding either. However, the PZ, which has A to U symmetry and was formerly non-bonding, can now interact via pi bonding with the LGOs that are perpendicular. Now the 2px and the 2py, which have EU symmetry, can interact with the parallel ligand group orbital, which is also EU symmetry. So that means that one of the ligand group orbitals, the one which has B to U symmetry, will remain non-bonding and will not be able to make any pi interactions. All right, now I see we are already over the time a little bit, and it will still take some time to construct the molecular orbital diagram of the entire square planar complex under the consideration of pi bonding. Therefore, I think it's better if we stop at this point It just